The natural world often appears simple on the surface. Beneath that simplicity lies a deep underlying complexity. The world by nature is chaotic and unpredictable, yet within this chaos there exists a hidden order, a simplicity that emerges from complexity. Without this balance between chaos and simplicity, life, as we know it, would cease to exist.
Hey everyone, welcome to Peter Looks, and today we're delving deeper into the fascinating world of mathematics and nature through Ian Stewart's Nature's Novel. In this final chapter, Stewart uses three component examples, Brops, dynamics, and Daisies, to illustrate how complex systems in nature give rise to patterns and structures that we perceive as simple. These examples reveal how mathematical principles are at play, allowing us to make sense of the seemingly random and chaotic processes in the world around us. The first concept in this chapter is Brops. Stewart focuses on how the shapes and the figures can be explained through mathematical principles. Small drops that those upon their water droplet on a leaf are known as spherical. This spherical shape follows surface tension, which minimizes the radius of the area. However, as a drop increases in size, gravity begins to play a significant role. The balance between surface tension and gravitational forces determines the final shape of the drop that falls.
Consider raindrops. Initially, they form spheres, but as they grow larger during their descent, they flatten and take on a more elliptical shape due to air resistance. This transformation illustrates a key point. The behavior of drops is not just about size, but also about the combination of various forces acting upon them. To visualize this, imagine a droplet on an inclined surface. At first, it remains spherical, but as it grows and the angle increases, it begins to elongate and slide.
The third topic in Ian Stewart's Nature's Numbers is dynamic chaos theory. It discusses phenomena like sensitive dependence on initial conditions wherein small changes in an environment or a situation can lead to vastly different outcomes. According to Stewart, changes in populations of interactive creatures are represented by differential equations. Even a small alteration can have catastrophic and anticipated results for that dynamical system. Let's use this marble drop experiment as an example. Let's start with setting up an incline using cardboard or a book and position it at an angle on a table to create a round. Place the marble at the top of the round, drop it, and observe and mark where the starting point to the left or right of the original point. Drop the marble and observe the change in the landing position. Repeat this procedure multiple times and note how each drop leads to different outcomes.
The third topic from Chapter 9 is Daisies. It discusses how Fibonacci numbers, a sequence where each number is the sum of the two before it, often appears in nature. These numbers show up in plants, such as the number of petals on flowers or the arrangement of seeds. They arise from mathematical patterns during growth, rather than being solely encoded in DNA. While genes control many aspects of plant growth, some features, like the number of petals, are influenced by natural laws of physics, chemistry, and dynamics, which lead to these recurring Fibonacci numbers. A sunflower is one example. A fully grown sunflower has seeds on its head. These seeds form a spiral formation, and if you count the spirals on a fully grown sunflower head, you'll often find the number of spirals winding in one direction matches a Fibonacci number, for example, 34, and the number winding in the other direction also matches a Fibonacci number, for example, 55.
Understanding the concepts of this chapter is relevant in real life because it reveals how mathematical patterns govern natural phenomena, from the arrangement of flower petals to the formation of raindrops. By understanding these patterns, we gain insights into complex systems such as weather, ecosystems, and even technological applications such as computer graphics and engineering designs. This chapter helps us recognize the balance between chaos and order in nature, offering valuable lessons for fields like environmental conservation, technology, and science.